what Cyberthon demonstrates is there are no boundaries. When you watch this event, you start to believe that is possible.
Welcome to the second Cyberthon lecture of this fall. I would like to welcome all the audience here at ETH Zurich, but of course also all the audience around the world that joined this session here today. I'm Roland Sigrist. I am the co-head of the Cyberthon project of ETH Zurich. Teams all over the world are preparing for the Cyberthon 2024, which will take place next October. On the road to Cyberthon 2024, we have different events. One of these event series are the Cyberthon lectures. We ask the Cyberthon community, the current Cyberthon teams and potential Cyberthon teams, which topics they are interested in, where we could invite experts to hold a lecture. We already started the lecture series last week. You can still re-watch the lecture of last week with Christian Bermes about how and why to win a Cyberthon competition. Today, I'm very happy to welcome two experts from Maxon who will talk about motors and energy supply in the context of assistive technologies. I would like to quickly introduce our lecturers today. We have Tobias Wellerdick. He obtained his master and PhD in electrical engineering from ETH Zurich in 2014 and 2018. Between 2014 and 2017, he was affiliated with the Power Electronic Systems Laboratory here at ETH Zurich. He was working on magnetic levitation. Following this, he joined Brusa, where he was involved in the development of electric motors and power electronics for e-mobility. Presently, he has taken on the role of the head of robotic drive systems at Maxon. His primary research interests encompass drive system, power electronics, and mechatronics for various applications. Tobias will hold this lecture together with Max-Erik Busse-Grawitz. He is currently the Technology Transfer Manager at Maxon. He holds a master's degree in electrical engineering, also from ETH Zurich, with a specialization in medical technology and radio frequency engineering. He also holds an MBA from the University of Maryland and GSBA Switzerland. Max-Erik's career started at Bruker Biospin, then moved to the Paul Scherrer Institute, and thereafter to CSIM, a technology consultancy at Alpnach in Switzerland. His work included, among others, work on robotics, controllers, amplifiers, artificial intelligence for optical pattern recognition, and for chemical analysis. He was also a part-time teacher at the University of Applied Sciences in Lucerne. At Maxon, he led the encoders and sensory group, built up the mechatronics group, and is now responsible for technology transfer, which involves technology scouting, consultancy, as well as partnerships with academia, high-tech startups, and think tanks. So we are very honored to have you here today to dive into motors and energy supply in the context of assistive technology. I would like to quickly announce that the audience online can use the Q&A function in Zoom to ask questions. We will have the chance after the lecture to ask these to Max-Erik and Tobias. And with that, thanks again, and we are looking forward to your lecture.
Thank you. Thank you, Roland. Thank you for having us. It's always nice to come back to come home to ETH Zurich, where both of us spend a lot of time in our education. Welcome to our talk, our lecture on motors and energy supply. Our idea here is today to give you some insight on what we think is a good way of selecting the optimal drives for controllability and efficiency. A quick outline of our presentation. We will shortly introduce Maxon. You see, we work for a company, we wear suits. Then we talk about outside-in versus inside-out technology. So the idea here is the environment defines the suitable technologies. Then Max-Erik is going to take you on a deep dive inside drive technology for unstructured environments. Then we're going to zoom out a bit again. I'm going to give you some ideas on how you can select the optimal drives. How do you get to the point where you can order something for your Cybathlon team? And the last topic, this is more aimed at students or people who think they would like to start a Cybathlon team. We have some ideas how we can support you there. Quickly about our company. Maxon is a company, we provide solutions for motion. Right, so we started originally doing motors. I mean, this is a non-exhaustive view of our portfolio, but by now we do sensors, we do electronics, we do multi-axis control, we do gears. So we have a very broad portfolio. Anything that you would like to move, we can help you as long as it's within the small voltage range. We're already introduced. I just like to add, we're always very happy to discuss new, interesting, exciting technology opportunities. And one thing that is sometimes a bit overlooked, Max-Erik is not just a scientist and an engineer, but he can also support you in how do you bring your idea to a business success. So we also try to help you there. Now, outside-in versus inside-out technology development. Before I go into the topic, short disclaimer, a lot of the topics we discuss here today, a lot of the lessons we learned in the past originate from our collaboration with Anibotics, so shout out to them. They're a fantastic company. We really enjoy working with them. We believe a lot of the lessons we learned are transferable to Cybathlon. That's why we're here today. But if you don't think so in the Q&A, please challenge our assumptions. So if you don't know them, check them out. They have amazing videos and a very cool product. Now, outside-in versus inside-out technology. It's all about the race, right? So this is maybe not the race you're in, but both of those systems are designed to finish a race as quickly as possible, to win, like Cybathlon. So the overall objective is the same, but they are very different. Why are they different? Because they operate in very different environments, right? And no one would come to the idea to take a Formula E car and apply it to a rallycross stage, right? It's not going to work, even though both are amazing technologies. So why are we showing this? One, because I like cars. I spent some time in the automotive industry. Two, it's very clear. No one would expect them to perform well in the other environment. So the question that we have is, why do we do this? Why do we use technologies that were developed in an industry environment and are optimized for an industry environment and apply them to Cybathlon? Or if you think where your technologies will go in the future, outside, right? Your pilots at some point should leave the Cybathlon challenge. You would like to have people walk around here on stage or in the environment, a very unstructured environment. So we believe solutions that work well on the left are not necessarily working well on the right. And this is what we mean when we say the environment defines the technology. So if you start to think about the solutions that work for Cybathlon, you should look at your environment you're operating in the long term. And you should compare it to the status quo, because a lot of people, when they talk about robotics, they think about industry robotics, maybe even without knowing them. They're biased to that, what they know. Now, we're not saying that robots in an industrial environment are boring or are not challenging. I mean, there are some amazing technological challenges, and Maxon is also active there. We're just saying they're very different to what you need, right? So robots in industrial settings, they work in a safe environment. What we mean with that is you cannot just walk into an automotive production facility where half cars are moved around by big heavy robots, right? It's protected. There are emergency shutoffs. The system will shut off if a human enters. This is different to Cybathlon or to any robot going outside of the protected environment. They need to be super precise, right? If you have a robot that assembles a printed circuit board, you need sub-millimeter repeated accuracy. If you walk with an exoskeleton outside, not necessarily. So the drive systems that were developed for these applications, they meet those challenges using specific technologies, and those are not necessarily the technologies that you need. So, applying this to Cybathlon, starting with the Cybathlon disciplines, we looked at all 8 of them, and to be honest, there are 3 of them where we, as Maxon, cannot really help you. We still like to discuss about brain-computer interfaces, no questions, but motors will not solve these challenges. The other 5, we might have something in our portfolio that can help us. And we would like to split those into 2 groups, right? There is continuous movement, driving around. That's a bit different to the other 4 disciplines, which are, I would call them, movements inspired by biology, right? So we will focus on the 4 on the left, and then I have a slide giving a bit a line on how you can apply this also to the wheelchair race. Now, to make things a little easier, we just focus on the exoskeleton in the first step. So what's special about an exoskeleton and about the environment an exoskeleton operates in, right? And in the end, what we want to do, maybe not next year in Cybathlon, but in the long run, someone with an exoskeleton should be able to walk like a person without an exoskeleton, or maybe at some point do more. Why can someone in an exoskeleton not run faster than an athlete without an exoskeleton? What do we need to do to get to this point? And we believe to answer this, there are some characteristics that you should keep in mind, right? Exoskeletons are battery powered. They need to carry their energy supply. An industrial robot does not. Drives in an exoskeleton are part of the problem, but they're also part of the solution. You have to carry your own weight of your drives. So if you have light and efficient drives, your job gets easier. A lot of movements is zero work. That is shared by some industrial robots too. I will go in a minute what we mean with this. Collisions cannot be avoided. Every one of us who has the fortune of being able to walk without assistive technologies, without an exoskeleton, we stumble all the time. We run into furniture. Collisions happen. How do we build exoskeletons that can deal with that fact? And precision is not critical. It doesn't matter if I stand here or 0.1 millimeters to the right. You're not going to notice, right? So you don't need the same precision as in an industrial drive. Now, quick and easy illustration. What do we mean with you have to carry your own energy supply? So the team on the left is not very efficient. Have a big battery pack, right? They have a lot of mass. They need strong drives to carry that mass. The team on the right has somehow found solutions to be more efficient, right? So your job gets easier and easier. So there is like feedback loops to make it even more easy, right? You have less cost, less mass. You need to you get easier control. You have less impact energy and so on. So try to be efficient. It's not so important when you are an industrial robot designer. Second one, zero work. So if you look at your Cybathlon disciplines, you start somewhere with speed 0, you do some task, you end somewhere with speed 0. So the energy state at the beginning and at the end is the same, right? So everything you expend in work, you can get back. If you climb up a flight of stairs, you will also climb down. So think about drive systems that are good in recuperating energy, because then you can make your battery even smaller. If you look at conventional data sheets, also our data sheets of motor drive systems for robotics, you only get one quadrant, the motor quadrant. But you also care about generator operation. So challenge this assumption that you're only looking at one part of the problem. And this is actually my favorite part, the collision part. As I mentioned, we run into stuff. In Cybathlon, you have a semi-controlled environment. You can do it in a way that you don't hit obstacles. But if you think where your technology will end up, hopefully in the future, the people that use it, they will have this problem. So what can you do? And we try to be light on the formulas here, even though it's ETH. This formula you all know, right? The kinetic energy in a collision is somewhat proportional to the mass and the velocity squared. So what can you do? You can build your system light, that works, or you go slow. You don't want to go slow, it's a race, right? So think about this and think if those super precise and heavy robot drive system for industrial are really the light solution that you need. Now the last point, precision is not important. I think I touched this. So looking at the other applications, and I'm not necessarily saying that what we write here is completely correct. So depending on what you do in the assistant robot race, maybe you need a lot of precision. Depends on your architecture, on the solution you go for. But ask yourselves the question, and as a good starting point, I would focus on the difference to conventional robotics, to call it like this. And then think yourself, okay, which technologies can I change? Which can I keep? How do I approach this? wheelchair race is a little bit different. Also, you can crash with a wheelchair, but usually the force and torque is not directly acting on your driving system. So driving is a bit different to walking. But again, challenge all these assumptions. Now, recapping this section, the environments are very different from conventional robotics to anything you use for Cybathlon. The question is, how do we select the right drive systems? And for that, the deep dive into uncontrolled environment, I hand over to Max-Erik.
Thank you very much for this starter, and now you will hear a little bit of zoom in into the whole thing. We will repeat ourselves, but it's a lecture, and good teachers do repeat things. So, other way around. Here we go. So, the first thing is that you have to say, okay, if you're in an unstructured environment, collision is part of the game. And so, as a paradigm, we could see these two football players here, and they have a conflict of interest, yeah, because their interest is to actually hit this ball over there, so they have the same goal, but there are some obstacles, and what happens is, first of all, okay, both will crash. If you do that with a robot of today's quality, normally the robots will be finished. And that's what you don't want. And why can't humans do that? First of all, we have our sensors on the outside, and we have the muscles on the inside, and there is a distance from the sensor to the bone. And this distance is covered with an elastic element. And so what happens is if our sensors are triggered, which is happening in this crash there, then everything in the body will go down in energy, so it will do everything to get rid of the kinetic energy if you want. And so that's the strategy of a series elastic actuator. So in principle, you can say auto robotics is nothing else but management of collision energies. Yeah? If you have a series elastic actuator of a robot with a very high inertia, you will need a very thick spring. Yeah? If a human being is very slow, he needs to have a very big body mass to actually absorb the collision energy. Yeah? Then the other things are also in auto robotics, because motors are part of the problem and part of the solution, that the local derivative, the partial derivative may be positive, but the total derivative may be negative. Yeah? So adding torque to your system is not necessarily a good strategy. Let's put it like this: a cat can jump up trees, an elephant can't. They're both built with the same technology. Yeah? So sometimes you may want to investigate if lowering the weight of an actuator actually helps. Yeah? And then the other things which you have to look at is, okay, you don't have a measure of your environment. You're not in an industrial environment where you know everything, but you know nothing in principle. The only things you have is your eyes. It's your ground reaction force sensors which are at your feet. You have the sensors, touch sensors at your skin. Everything of that has some kind of delay. And so you need also very benevolent ballistic behavior if you want. Okay. And it's clear that, but that's your thing to solve, that you have to have a good task hierarchy and that you have to design for collision tolerance. And so let's say we have two paradigms. One paradigm is the industrial robots, which are precise and where the motion pattern is in principle limited by technology, so you want to be as fast as possible. And in outdoor robots, actually, you don't know what's happening, and so you don't want to be as fast as possible. You don't just run around here in the ETH if there are other people, yeah, because you would crash into them. And so the kinetic energy is not limited by technology, but it's limited by the collision scenario, which would be probable. And the other thing is you don't need the precision. And for that reason, for example, even if you want to be precise in a way, the question is, do you want total precision or do you just want local differentiability? So do you just want that your Jacobian and your robot exists? And oftentimes, if you have your gravity assisting you, all gears, even if they're play, are in principle in a pre-constrained state, and so you have local differentiability without actually needing to have a very precise and very inefficient gear, which would be probably a strain wave gear, which was optimized exactly for the industrial environments, which we don't want to talk about. Okay, so you see those two paradigms, and that means that you want to have impedance control, not necessarily position control, and you want to have some elastic elements and not necessarily something which is super stiff and super precise. Now, the question is, if we say we have to limit impact energy, how do we want to do that? First thing is get slower. We have said already that is not really the strategy that you want to follow. And then the other thing is you want to look for motors with a low mechanical time constant. And you want to ask, yeah, what the heck is this? And the easiest way to explain a mechanical time constant is that you say it's the thing that links the motor constant, which links the force of the motor to its inertia. Yeah, so if you have a certainly relationship between torque and inertia, and normally the inertia is proportional to the square of the torque. And that's more or less a technology parameter. And so, if you want to go down with this here, you go for motors with a low mechanical time constant, and not for the motors with the highest torque density, for example, which is often a design error committed for outdoor robotics and which leads to very bad results. Then the rest, I think you know, friction clutches are always good, or something which self-destroys at a given point and where you can reassemble, yeah, so magnetic couplings or whatever you want to have there. Lightweight design is a no-brainer. Use of tendons is something which humans have at perfection, and we'll go to that later. So putting the inertia where it doesn't hurt is a very good strategy for all kinds of robots. And then SEAs, that's clear, it's also a non-brainer for the audience, I think, and even elastic padding. And one of the things which is a strategy which is often used, but not so much seen in Cybertron, I think, is that you say, my elastic hull is also a sensor. Yeah, so if you have an elastic hull with a pressure sensor or a microphone, it can function like a piece of skin where you really can then make collision damage, let's say, mitigation in time before something happens. Okay. And so what do competitive robots require? There is always something where you have the engineer, you have the economist, and on the other hand, you have the real requirements. And most of the time, I think people want to spend as little as possible on sensors, which I think also, if you look at what has happened in exoskeletons, for example, 10 to 20 years ago and today, I think very decent exoskeletons will use ground reaction force sensors because it's nearly impossible to derive your state without a GRF, for example. So get more sensors, get meaningful sensors, and please sense what you want to measure, and perhaps spend more sensors. They are not so expensive today anymore. Yeah, so that means, for example, having an IMU is much better than watching the motor current, which I would say is a poor strategy. It's always helpful, but try to also measure accelerations if you're interested in accelerations, or if you want to measure the body state, have good encoders, decent encoders. Okay. And it's clear that for robots, drive selection is not completely trivial. That's the reason why we have more than one motor. If there was the best motor, we would have a catalog with one motor. Life would be easy and really terrific for us, but alas, it's a little bit more. And so you see the selection criteria. I don't need to read them aloud to you, but it would be something where you really want to balance out all the things. Normally, for a Cybertron environment, you would like to go for motors with low mechanical time constant. The other thing you want to look at is also the losses at higher speeds. The third thing you want to look at is at gears with very high efficiency, and I will come to that later. Now we can make a deep dive and say, okay, what's happening if we want to go for movements with zero work? And with movements with zero work, as we've mentioned before, efficiency is not exactly the criterion you want to look at, because efficiency is by definition zero. Yeah, you have done something, you have done nothing, but you have spent something on it. Yeah, so you go to Olympic discipline, you have the 100-meter race, and the people are quite exhausted afterward, but you can tell them with a good conscience that they have committed zero work, so actually you've got a gold medal for doing nothing. And so, okay, what is here the figure of merit? And the figure of merit must be something like the energy spent for a given task. And the given task could be something like moving a mass by a certain amount of meters in a certain time. So if a mass, a distance at a time, or you can say also in rotatory coordinates, it would be something like moving an inertia, rotating an inertia by a certain angle in a certain time. And the first thing is, okay, if you want to minimize your energy, you want to optimize your gear ratio, and you know everybody knows the formula that you adapt the gear ratio to the impedances, and so you take the square root of both impedances, and then you divide them, and that's the gear ratio. And the other thing is you want to use a 1-to-1-to-1 trapezoidal profile for this kind of motions, or ideally a parabolic profile, but it has some other drawbacks. So normally in industry you will go for 1-to-1-to-1 trapezoidal, but your mileage may vary. Okay, and if you have done that, you will find out that your movement is limited by this formula. This formula is not really published. I always say it's kind of too easy for a professor, because you cannot publish this because it takes about 20 minutes to derive on the back on an envelope. But also it's too complicated for most engineers because they don't have any idea about motors today. So I give it you for free, this formula. And it's in principle the copper losses in the motor are in excess of 54. That's due to the trapezoidal profile. So for a parabolic profile it would be 48, and that's the total minimum. You can do calculus of variations if you don't believe me. And then you have something where you have delta t to the 4th power. Yeah, and it seems implausible, but let's put it like this. If some untrained person goes to lift weights, and if you go to the Olympic Games and you play the same thing with the same persons, then you will see that the persons with the same weight approximately are 4 times stronger if they're well trained. And if you do running, what you will see is that an untrained person will run at, let's say, 14 seconds, and a very well-trained person will be doing that at 10 seconds. And so you will have here exactly the same 4th power. It's also there in biology. Yeah, so you take the square root of 2, the square root of 4, I mean, and then again the square root, so the 4th root of 4th gives you the square root of 2. That's exactly a ratio of 14 seconds to 10 seconds. So they have a speed limit here, and doing things faster in robotics will be highly penalizing. The other thing you will see is that we have the famous time constant, again here, and the other thing what you see is the gear efficiency. And we will dive into that later. First of all, I said that the mechanical time constant is a technology parameter. And what I mean is this, you have a quite scale invariant thing here. So we have all the motors of our catalog are summarized in this graph here. And you will find out these old motors and the flat motors were here, and that was about 60 years of innovation brought us from here to here. And you see this proportionality, and by the way, the proportionality is maintained if you apply gears. Yeah, so applying a gear doesn't change things. You augment the torque, but you also augment the inertia by the square of the gear ratio. So you cannot exceed that. So this double logarithmic graph, you can barely see the axis, but I hope you can see the grid a little bit. Okay, and what you see is that here this relationship holds true over a large range. So in principle you can say a motor which weighs 2 grams or a motor which weighs 2 kilograms with the same technology, with the same engineers, gets the same mechanical time constant. It's a miracle, I don't know exactly why, because all the partial derivatives are something which was pointing up or down, but the total derivative seems to be 0. Okay, now, since we cannot change too much about our reality, let's say what can we do here? First thing is you can say, okay, I want to minimize energy, I work on the problem. Yeah, because that's the most obvious thing to do. So how can you work on the problem? Minimize inertia. How do I minimize inertia? We have said use tendons or use lightweight design. The other thing is you can use resonators. Yeah? So for example, insects, their wings are resonators. Yeah? And this is much better because if you had to flap every time, that would be quite expensive, motion technology made. And that's the reason, for example, you have wheelchairs. Yeah? A wheel is nothing else than a resonator. Yeah? So instead of accelerating, decelerating all the time by walking, with a wheelchair, it is not accelerating, decelerating all the time. It's the same strategy. It's just not so good for unstructured environments. Then we can work on the motor. And the motor, it's very easy. Use a low tau m. And there with a certain caveat, if you only go for tau m, then the motors might be a little bit lossy. So you want to use a well-balanced motor. For example, in our case, it would be what we call dynamic torque motors. Then the other thing is you can work on the gear. And the gear efficiency is super important. And we will go to that back later because it's even more dramatic than that, because that is related to copper losses, but there are other losses too, for example, in the gears. You can also use belt drives, and belt drives are normally very efficient, and so that's something I would also encourage. So use sinews, use belt drives, or whatever you have, timing belts, yeah. And, well, in nature you see a little bit that we have exactly what we talked about. So we have very low friction. We have extremely good and optimized dynamic range. So that means because of the low friction, actually, we can, for example, lift up a feather without destroying it, a bird's feather, but we can also chop wood with the same hands. Yeah? And that's something which is related directly to friction. So low friction gives you, in principle, robots that are good to interact with the environment. And then the other thing you are looking at is very low inertia. And as we said, we have muscles with a very low mechanical time constant. And the other thing is that the muscles are always located away from the actuator. Yeah? So we do have the muscles that actuate on the hands. We have them here and not at the hand itself. So otherwise the hand would be inoperable. And well, if you have to use human-made technology, what are you doing then? Well, choose motors with low friction and with a low mechanical time constant. And friction, I mean not only mechanical friction, but also magnetic friction. So look at the working points and how lossy they are here. Look at gears, which have very low friction. And low friction sometimes contradicts other things. For example, you get only low friction with higher play, and for that reason there's a lot of gear innovations going on, because these conundrums are solved different ways. Also, you pay a weight penalty if you want to be, for example, overly efficient or overly collision tolerant, and so oftentimes gear weight and the weight of your spring systems will go in a total system simulation. Okay, with the sensors, let's say you can use encoders, you can use force torque sensors, like for example Botta system sensor, who are our friends here, full disclosure, but I don't have any shares. But I think their idea is very nice, that they have a 6D sensor, because then you can do matrix gymnastics and you can project the force to whatever point you want in your robot, which makes absolute sense. But you can do the other way around. You can use, like the Komuro lab has been doing already 15 years ago, just a sponge which is electrically conductive and which acts as a touch sensor. Super low cost, super effective, and the sponge is at the same time also the elastic element of a series elastic actuator. And, come on, controllers, they need to be fast, 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 even if you are doing slow movements, because you want to do impedance control, and the impedance range is directly proportional to the speed of the controller. So if you have a controller with a control speed of, for example, for position control, 2.5 kilohertz, then at 20 hertz, which interests you more, you will have a dynamic range which will be plus or minus a factor of 100. Okay. Now, we want to adjust for reality, because oftentimes you cannot choose. Let's say, for example, you have a robot which has a zero kinematics, and for example, you want to have a gripper which grips something for your wheelchair and does something. There are some cyberlon challenges about that. If you have zero kinematics, what gear actually do you use? Because here I have a completely different inertia than at this working point, or than at this working point. Same holds true for exoskeletons, so the inertias are very much state dependent. If I'm here with my leg or here, I have a completely different inertia. What happens if I cannot do that? The other thing is, what happens if I have friction? And what happens if gravity is important? Because we said zero work, but if I have to stand here, I have to already support my weight. So what can we do here? First of all, reduction ratio. I have a good news here. So, if you miss the reduction ratio by a factor of 2, the penalty what you pay for energy consumption is only 25%. Which means, in principle, you just stick your thumb out, you say, okay, I take this inertia here, I take this inertia, you take a kind of a middle value, some medium value, some expected value, you shoot for that, you take your gear reduction ratio for that, and then if it ever so happens that your inertia is a little bit off, you essentially don't care. That's a good thing. Gravity, same thing holds true here. So if you have a scenario, especially for exoskeletons, where gravity is dominating, then you will want to have a higher gear reduction ratio. And if you have something which is the average of the gravity divided by the average of your other accelerations, I could call that a gravity acceleration ratio. Yeah? Then you have to adjust your gear reduction ratio and see that in that graph. And so you see that, for example, if gravity is dominant by a factor of 3, by a factor of 3 like this here, you will want to adjust your gear reduction ratio by a factor of 2. It's a rather complicated calculation that leads to that thing here, but here you can just use the graph to adjust that. Gear efficiency for zero network is a completely different piece of cake here. Because actually gear efficiency not only hampers your movement, but it also hampers recovery. And for that reason, gears will get very hot and will make very hot drives. Typically, what we use in the industry would be strain wave gears, and they have typically an efficiency of 60%, if you're lucky. Now, let's go to some other planetary gears which are highly efficient, with good roller bearings, which we have, for example, cranked out, especially for the robotics industry, for auto robots. Then you go to something in the neighborhood of 90%. So look at this here, and then you see, okay, I'm wasting something like 1.2 or 1.3 with respect to an ideal gear, and here you're at a factor of 4. If you divide those numbers, you are something in the neighborhood of 3. So going from a strain wave gear to a highly optimized planetary gear will save you a factor of 3 of energy. And that is not something which we just claim. It has been also proven in some robots where, let's say, strain wave gears have been replaced by the other thing. So that's a thing to look at if you are designing something. And now I hope that I can, yeah. And let's now look at an example of somebody who did really everything right. So the first thing is what you're seeing here is that the motors are at the shoulder. You see the motors here. The motors are actually very small. They're inner runners with a very low mechanical time constant, and also with cooling ribs added, because the cooling ribs don't add to the inertia of the robot, so you can even dissipate more heat. The thing is extremely low friction. For that reason, it's completely backdrivable. You have everywhere those steel tendons, which are super efficient, and the steel tendons are at the same time force transmission and also force reduction. So you have different roles with different reduction ratios that do that. What you also see here is the kinematics themselves are quaternion kinematics, which are easy to calculate, and they're super low friction. And so at the end of the day, what you have is the result that the robot is very low inertia and for that reason very collision tolerant. That would be the end of a classical robot, and hitting the arm with that frequency with a classical industrial robot would normally invoke the call of a service technician, yeah? Or would trip the robot. And so with that, I think I'm done. Up. Come on. Yeah. Here. And back to you.
Thanks
for more details.
Yes. So now you have an idea on the technology. But in the end, 2024, 2025, 2026, Cybathlon goes on. You have to put something on stage. So how do you go forward? How do you get to the point where you can go to an online shop, call Max Erik and say, I have a cool idea, please give me the drive for free. He might do it. How do you have to tell him a number, right? How do you do this? So different example here. So this time we go for the assistant robot race, and the team decides, for whatever reason, we're going to build our own robot arm. Cool idea. What do you do? Step one, you go, you watch next Thursday, I think, right? The user-centered design lecture, right? So this is obviously your starting point. Then you just start to define use cases for your robot. You say, okay, this thing has to pick up an apple and move it to my pilot. You have payloads whatsoever. You do your job, right? You define an idea for your robot. How big is it going to be? So on. And you do a first calculation about the torque and the speed you need at each axle of your robot. And because you're engineers and with an ETH background, you probably do a simulation to do this. And that might look something like this. So you see the robot moving here on the left, and on the right, you get for axis 2, can be any axis, you get the speed of the joint, the robotic joint, the acceleration and the torque. And then what people usually do, they say like, oh, all right, we need here minus 40 Newton meters. They take this 40 Newton meters as peak torque, they go to us and say, I need a 40 Newton meter drive. And all that information that is here that you already have for free is lost. So don't do that. Come to us with the whole time series graph, and then we can discuss. Maybe 40 Newton meters is only used for a short time. Maybe we can use a cheaper motor. Keep that in mind. You now have an idea about the torque and the speed. Maybe you have a mass idea from your team of your drive systems. What do you do, right? So select the drive systems. Easy, right? You go to our homepage or competitor's homepage, hopefully not. You open it up and you find the hundreds of drives, electronics, and gears. What do you do, right? I mean, it's exhaustive. You need some electronics for your drive, you need a motor, you need maybe a gear. Maybe you decided you don't want to go direct drive. We grade out the sensors, and you have the problem, I need to have an ordering number for my electronics and my motors. How do I do this? Well, we look at the technology, what Max Erik just told you, right? You look at the different motor types, you can maybe go to literature. We have some publication also on our homepage, and you figure out, okay, some motors are more well suited to my application than others. And you figure out, for whatever reason in this example, all right, I want to go with a so-called frameless motor. They're nice in integration. There are these dynamic torque motors that Max Erik showed on the top right graph. Good tau-m, good torque, good speed, and so on. The thing is, we have 8 of those, and we're one company. Obviously, we believe we're the best, but other companies also have cool products, so you still have the problem. You have quite a large solution space. How do you solve this problem? I mean, you're going to do the same with the electronics, with the gears. Now here, we use a strain wave gear. Maybe your application requires this precision. Let's see. And we limit ourselves only commercially off-the-shelf components. And what you see is, example, 8 motors. We have about 3 electronics that fit to that. 3 gear options. This would be another supplier. You already have 72 options. How do you get to the one optimal solution? You can try and error. Good luck. It's going to be a lot of fun. You have a lot of drives lying around, but it's going to be costly. I don't know what the sponsoring is of your team. Ask experts. See what worked in the past. This is a good idea. You can try some other stuff, but in the end, you need some sort of a systematic optimization to select the optimal drive for your application. And we do the same. So we also do this for industrial customers. We sell this service. What we do is we take a model-assisted approach. So we have models of our drive systems and of our competitors' drive systems. We simulate the performance of the drive system. We select the best suited drive system. And at some point, or some of this already works, you have a closed-loop optimization. If you do closed-loop optimization, call it AI, you get more sponsoring for your team. Now, how do you get this, right? I mean, you don't have a measurement lab at home. You can probably not characterize different drives. Well, use the data sheets. A lot of information is available, right? So how do you build your drive library? There are different ways of doing this. And what I would maybe take here as a message, be simple. I mean, I know that myself, I also attended here. Engineers from ETH have this tendency, if you can model some physical effect, we're going to do it, because it's cool, it's interesting. But the thing is, it just takes a lot of time. And what we show here are 3 different options of how to model a motor. The one on the left is all values you find on our data sheet. You can do this in an afternoon, in a little Python script. You can do it in Excel if you want. The one in the middle, don't go into the formulas. You can also do this with our data sheet, maybe 1 or 2 phone calls to your motor supplier. Of course, it's going to tell you more, but really ask yourself the question, what accuracy of model do I need to answer the current state? And then you can drive this to exhaustion. You can do a PhD on these kind of topics. So keep it simple. You can already do a lot with very simple models. And I give you an example of what you can do. Now you can read this yourself. I mean, there are some things you need to be able to do, right? Your model somewhat needs to transfer inputs, like current and voltage in this case, to torque and speed. And as Max Erik mentioned, there is nothing for free. You will have some losses, but that's about it. You don't need much more than that. Now, giving you an example, right? We're building a robot. We decided we need around 150 Newton meters. We selected Maxon because we like the logo, we like the products, whatever. We selected 4 drives. I mean, actually, we looked at more, but there are 4 candidates which are reasonably close with a gear ratio of 1 to 100. Right, so which one do you take? Okay, none of the motors really fits your torque speed requirement of 25 RPM, 150 Newton meters. So you have to drive those points here. Well, if you have an approach with a very simple gear model, and in this case the gear model is just a ratio and an efficiency, you can start to play around, right? So we start these 4 trajectories here. are the different motor types. We start with the 100-to-1 ratio, and for the small motors, we increase the ratio to get more torque out of the system, and with the others, we start to decrease the ratio. Now, last slide, we would have probably picked the lightest motor. But the thing is, with the lightest motor, we're not going to get to the sweet spot. There is no gear available. I mean, of course, we can have a customized gear, but we're always going to stay a little bit below the target torque. With the heavier motors, we can get to the required torque. I mean, you can always use a motor and drive it slower. You pay in mass. But what you can do here is with very, very simple behavioral black box models, you can identify trends, and then you can go to your team and say, all right, can we afford a more expensive, better cooling system and overdrive our motors, get more torque out? Or do we say, no, it's better to use a bit heavier drive? We pay the price in collision energy, but we have a simple cooling system. So very simple models allow you to identify trends which you don't see if you only look at the data sheet. Another benefit, if you do this early in your project, it's de-risking. You know you looked at all the options. You know that not shortly before the competition, someone will come with a genius idea and you overlook the drive because you look at all of them. Next thing, remember I told you to keep this in mind. What you can also do, if you have a model which can visualize you the behavior of your drive, you can do something like this. So we translate the torque and the velocity to this potato shape here, which is just the speed of the drive and the torque of the drive over time. So your little robot is moving, this is the torque speed. And now you can compare to the limits, right? So the green lines here is the current of your electronics. And you see, okay, maybe you have an electronic with 5 amps of continuous current, you have an intersection here. So you go talk to your electronics expert and she tells you, look, this is not a problem. You do this for a couple of seconds, my electronics can do this, you are in a short time overdrive mode, no issue here. Next, you talk to your battery guy. This is the red line. This is the power supply to the system. And you tell the guy, look, I need 100 watts for this movement. And then he might tell you, like, okay, at the beginning, when my state of charge is full, no problem. At the end, I might have a problem when I'm in a deeper SOC. I cannot pull this power anymore. So you can start to talk to this person, say, I really need from you this power. Please size your battery. We also look at losses. When this blue line is the cooling line, you can talk to your people like, do we need a fan or not? And the person will say, like, no, it's an aluminum design, 50 watts, no problem. So you can look at a lot of data, and you can go and deep dive in one option and really look at what are the limits, the limiting factor to my drive. Summarizing, keep it simple, but do it. Don't just go in data sheets or call us and say, we build a robot, we need a 40 Newton meter drive. Be free to share with us this data. We will also challenge it if you want. Simple models bring you a long way. Don't go really crazy. Predict the performance early in the design. De-risk your designs. In the end, you have a hard date. When you have to be finished, like I'm with my presentation now, have to be finished, you have to go and put your exoskeleton on stage, right? So if you de-risk early, you have less sleepless nights shortly before Cyberthon. And the last point is really, simulation design is good, but it's nothing without reality. And this is really where your previous projects come in hand. Recalculate your previous projects compared to measurement to calibrate your simulation tools, because only then you really have meaningful results. Last point, Young Engineers Program. I'll do this quick. So this is aimed at the people who think of entering Cybathlon. We like to help you there. We can only help you on drive system, but it's a very low entry barrier. So you sign up, it's an online form, it's also in this presentation. From us you get drives at a reduced price, sometimes for free, and the important thing is you get access to technical support. So we talk openly to you, we can also help you in other topics maybe, but it's really a cool way of talking to us, and we really like to support Cybathlon, not just the competition, but also the team. I just have 2 examples, one in Canada, one in Greece. This is a worldwide program for us. Probably at the end, you're still just going to talk to Max Erik, so it doesn't matter where you apply from. All right, this concludes our task. The take-home message is environments define technologies. Be careful about the biases you have in the back of your head, or your professors might have, because they spent 20 years doing industrial robots. For unstructured environment, think about the inertias, the elasticities, and the friction. Think about biology. And the last part, invest enough time early on in thorough system optimization. Don't just start because it's cool to have hardware on the table. make sure you get the right hardware. This has been our talk. I think now we are Q&A, right?
Thank you so much, Max-Erik and Tobias, for the insights that you gave us to the audience online and also here in the lecture room. Also here in the audience, you have the opportunity to ask questions with the microphone. If you have questions, then of course online you have the option to use the Q&A to ask questions. Maybe a first question from my side is a very general one. So if you could accelerate a certain development process of the components you use in assistive technology, what would it be? Is there the largest gap still in the hardware, in the software, in the control? So where would you like to have a push, if you could wish?
I think software did a lot of advances in the last couple of years, and what we observe is teams have really cool software solutions, are applying really cool control strategies, and then they're applying it on 10-year-old hardware. So I think the homework is on our side. We have to ensure to provide the hardware which is as advanced as the software in the last couple of years. Mm-hmm. So generalistic hardware development is too slow at the moment.
Yeah. I would like to add here the notion of explosive motion. Normally we are able to deliver 10 to 15 times more force in emergency situations than you would have in normal situations, and robots normally are designed for 1.5 to 2 times the excess torque. So I think there is a lot of research to be done, and also in terms of hardware, for example, that controls are overdimensioned in a way that they can support for, let's say, for example, half a second, 10 times more current. Yeah, there I think there's a lot of things where people are too cautious, and that at the end of the day you lose usability. So that's one of those hidden treasures. And the other thing I already mentioned, I think sensor development and sensor integration and sensor communication, so not having to have a cable for every single sensor. I think there a lot of innovation wish lists would be there, and I think there are some things to come also here.
Do we have questions in the audience? Yes, please, you can use the microphone. You have to click on it.
Yeah, thank you very much for the beautiful talk. I can really relate to this as a designer. I built also a working robot starting from motor, so coming up with the gear ratio, transmission, so on, so the full experience. My question is, we are seeing that the trend for the gear ratios to go lower, very differently from the previous industrial design. Do you foresee the motor changing and adjusting to a much lower velocity and changing the electromagnetic part to adjust to a lower speed regime and higher torque requirement to keep the inertia low? So to change the morphology a bit of the motor to really transfer part of the function of the gear ratio directly at the electromagnetical circuit?
That's a very good question, which I get asked oftentimes. And the simple answer is that the torque density, which you're alluding to, is a technology parameter. Yeah. So also torque density is very difficult to be influenced outside of technology. So it can go up in pole pairs, for example, with a motor. You can make a bigger diameter, but then you will still add weight and you will add inertia. So you can go for maximum torque density. Normally you pay with extreme inertia, and the mechanical time constant of those outrunners, which we're alluding to here, is so bad that normally for a robot you will essentially break the gears, and that's what you see also in many of these things. So, okay, for that reason they go lower in gear ratio. But then the motors get exceedingly hot. And so the same robots we are talking about here spend 280, 500 watts per joint, which is not reasonable in a Cybertron environment because you're close to humans and you want to stay cool. And so for that reason, I would say that it would be a much better idea to manage inertias. So to go for motors with low mechanical time constant and to go for extremely efficient gears, even though you will have to go a little bit more up in gear ratio. And normally what is really hurting with a gear ratio is the number of stages you have. So typically what you would do is you go to the highest gear ratio you can pay yourself with, for example, 2 stages. Yeah, that's a compromise you would be willing to take. Yeah. And otherwise also talk to us, because there are many things which are not in the catalog which we can do for customers. Yeah. So there is a lot of design space here. But to make a long story short, I see these tendencies to go for one-stage gears and then for exceedingly overloaded motors with essentially no air gap, and then the first thing that happens, the motor gets hot and then the motor gets stuck. Yeah? So if you want to be reliable, you need a certain air gap, and then in principle everything is a technology parameter. Yeah? So it's clear you can make a pizza, you can make spaghetti, there's different approaches to these things, but once you're stuck with pizza, then you can optimize it, and that at the end of the day you're stuck with Maxwell. And as far as I understand, there's no Maxwell 2.0. I am longing for that, but I'm still working with Maxwell 1.0. Yeah.
Other questions? Yes, please.
Thank you. Thank you for the nice talk. Cannot hear me, right?
And you have to click on it.
Light should turn red.
Yes, now you can hear me. Thank you for the nice talk. I have 2 questions. The first question is, you probably saw the previous Cyberlon competitions and also saw the different solutions that the engineers came up with when designing their assistive devices. Did you also see selections, like choices of motors that were surprising you positively or even negatively, let's say, where you thought, oh, okay, this was probably not well selected for that task, or the other way around, where you thought, oh, that was a nice idea to go for this drive selection for this challenge?
I have to say in all humility that if I look at the last challenge I've looked at, technology was kind of secondary, and what really was user experience. So in all humility, I have to say, look, I would be happy that the motors were the limiting factor, but I've seen really bad motor designs, but still winning because the user experience was much better. So that is my take-home message here. But for the next Cyberthlon or the next Cyberthlon, then perhaps we're talking about that. At the moment, for example, if you have a wheelchair with an assistive robot there, and the robot uses strain wave gears, which everybody used, it's so slow today that you essentially don't care. But once you do care, and once you want to be fast, and once things become more competitive, then everything which we said here should be applicable. And this lecture is more or less intended also for the Cyberthlon guys, not only of 2024, but also the beyond that, I would say. Yeah.
Yeah. I think we also have to be fair, right? I mean, Cyberthlon teams operate on a budget, and for me it's always very impressive what technical solutions come up. But if you can buy something off the shelf, and that is the only option, you're going to make it from a time budget and a monetary budget to the Cyberthlon, then do it, right? I mean, we're in no means trying to criticize this here, but as Max Erik said, if you have the time and if you think at some point the technologies from Cyberthlon will go to the outside world. I mean, no offense, but we're not doing it to win Cyberthlon. We're doing it in the end to bring the technology to the outside world. And then we will have different budgets, we will have different time scales, and then we might challenge some of the development approaches taken. And what I also, maybe last point, sometimes it's just a part of sponsoring. You talk to a team, and I'm not naming anyone, and say, yeah, these guys paid our team, so we use their technology. All right, fine, do it. It's great that you're here.
Yeah. For us, it's a great way to learn, actually, about the future market.
Second question, you had 2 questions, right?
Yes, thank you.
Thank you.
Thank you for the answer, which was also a nice teaser for next week's lecture regarding user-centered design, actually. Mm-hmm. Second question is, we're talking about the environment and knowing the environment. We always try, or Cyberthlon always tries to challenge different environments that the daily living is happening. So this gives some time, or comes along with the problem that you have different cost functions, different targets that you have to select your motors. Maybe you can also give us some advice in this direction if you have maybe also contradicting environments that you have to work in.
Yeah, I mean, obviously in the end, it's always a compromise, right? So there is not one optimal solution. I mean, it's not like the Formula E race we showed where the environment is stable for the next 10 years to come. This is clear. I mean, you keep the teams on their toes, right, by changing some of the environments and imposing new challenges. But that's also a cool way of, when you think about the next generation of Cyberthlon, the environment will change, yes, so then I would say the normal tendency is, okay, we already have something that worked well in the last environment, it's not going to be so bad, we're just going to keep with this, and we do incremental optimization. And if you are dealing with changing environments, our ideas or our call here is go back to the drawing board and really think, okay, what change do I really have the right technology? Because if you're on the wrong technology, you can improve as much as you want, you're not going to get a good solution in the end. So this is true, but I mean, this also makes Cybathlon interesting, right? Because Cybathlon 2020 and 2024 are different, and 2028, I don't know if you want to comment on this, but will be different again, right?
Of course, we always have new challenges to push the development of the technology, so we are brainstorming already now what we will do then in 2028.
But no information.
No information.
Let's say this, I think especially we as engineers have a tendency to be in control. We want to be in control. And so I see, if I could say which tendency I would try to pursue, less engineering for stiffness. You know, I think most things are overly stiff and overly heavy for that reason. So if you can say, how much stiffness do I really need, be it for exoskeletons, be it for external arms, be it for whatever it is, and can I save on that, and then can I save on the motors, can I save on the rest, can I put in some internal damping so that I don't get the oscillations, thinking kind of system-wide optimization, that's something where I see tendencies, yeah. Mm-hmm.
So we have a question from the audience online.
Exactly. Benedict is asking, and first thank you for the interesting talk, and then asking regarding the gravimetric torque density of the motors, is Maxon looking at different concepts such as axial or transverse flux machines?
Mm-hmm. Yes, we are definitely looking at that. We have been looking at that already, let's say, 15 years ago. So it's on our radar. Actual flux machines are super interesting because they have a super low time constant. However, the flux is guided in a way which is very unfavorable, so they tend to be super lossy. And the other thing is that you have very high internal forces. So actual flux machines, for example, for elevators are one of the best technologies. For robotics, we are still not sure if it is really something which leads us to where we want to go. But we are open to that, and yes, and transversal flux machines, same thing here. It's a poor flux guidance here, which in principle gives you the best torque density for, or bang for your buck if you want. You can make very cheap motors, but they will be super heavy and super high inertia and very lossy. And for that reason, we would say for Cybathlon, it could be perhaps not the best technology unless somebody comes with an architecture which I've missed. So we're always, open for things we have missed, but yeah, that's my take, at least with my knowledge here that we have here. Mm-hmm.
Come to us, Benedict. Let's discuss. Keep in mind what we have on our homepage is only around 20% of our catalog, so most of our drives go in customized projects. We cannot show all of them, but we can certainly have a discussion. And yeah, it's a niche at the moment, but if you have the great idea, then sure, we can help you industrialize, no problem.
All right, any other question here in the audience? Otherwise, I would like to thank Tobias and Max-Erik again for the very interesting lecture and giving us the insights and giving the teams also kind of a checkup list and a lookup table. So the lecture is also recorded. It will be online on Monday latest, so you can watch it again. We'll shortly go into an outlook of the next Cybathlon lectures, but for now, I would like to thank Tobias and Max-Erik.
Thanks for having us here.
Thanks for having us. Thank you.
So we will have Max-Erik again next week on Thursday together with Jan Meyer. They will talk about bridging the gap between human-centered design and technological implementation. So we heard it also today. User-centered design is very important, how to work together with the end user, with the pilot in the case of Cybathlon. And I would also like to announce the next Cybathlon competitions that we will have in February. On February 2, we will have the Cybathlon Challenges, where we invite all the teams to warm up then for the big Cybathlon in October 2024. Follow us, watch it online, or also be on site, of course, then in October. And with that, I would like to thank you. See you soon in the next lecture next week, and have a good rest of the day. Thank you.